We're starting section 4.7, applied optimization. So far, we've learned about derivatives. We learned about all the methods to find maximum, minimum, and inflection points, and all of those. In this section, we're going to use the three methods that we used to find either absolute extremums or local extremums. So what are the methods for the local? For the absolute extremum is the closed interval method. If the function is continuous and it will attain its absolute max or min between its critical numbers or endpoints. And so you find all the critical numbers, you find the endpoints, and you plug it into the original. Whichever is the max is going to be max, whichever is the min is going to be min. Then we may use first derivative test. Let C be the critical number of a continuous function. And then if f prime changes from positive to negative, and then C is a local maximum. If f prime changes from negative to positive, then we have a local minimum at C, and if it doesn't change, we don't have any extremum. Second derivative test, this time f double prime has to be continuous, and only the critical numbers that give f prime equal to 0. So f prime of C has to be equal to 0. Then if f double prime is negative, there's a local max. If f double prime is positive, there's a local min. What are the strategies to solve optimization problem? A lot of times, especially with engineering problems, you want to draw a diagram and find fixed notation for the entire problem. And so you have to figure out what you're optimizing. That's important. That's called objective function. And what are your constraints? Whatever you're optimizing, you have a certain set of resources, and that causes a constraint. And so you want to find that constraint. And then you want to find what are the constants and the variables of the function. What is the domain? Domain is very important because however the test that you're using, first derivative test, second derivative test, or the closed interval method, you have to have this domain thing worked out. So you figure out how you're optimizing or on what test you're using, and then you want to use the constraint to rewrite the objective function in terms of one single variable. Calculus 1 is all about one single variable, and so you want to use again constraint to do that. And we've been doing this in pre-calculus pretty often, but now it's more and more of that. Then you use calculus to find the absolute minimum and maximum of the objective function on the appropriate domain. Example 1. A piece of wire 10 centimeters long is bent into a rectangle. What dimensions produce the rectangle with the maximum area? So how does this work? So let's say wire is as long as AB, and then you have you're building that length rectangle. Basically, you bend it down into a rectangle. The blue rectangle is the rectangle whose perimeter is equal to AB. So if you move this around, you see that it can get as thin as 0, and I can get all the way to here again as thin as 0 area, and then and you get the different values. You can see the different values that are appearing on the bottom. So let's figure out when we have the maximum. Look, even with looking at this, you can see at some points it's getting bigger and bigger. And then you can see that after a point is passed, it starts getting smaller again. And so that's then let's figure out what value makes this the maximum. So let's start with drawing a picture. So we have this piece of the wire, and we're bending it into a rectangle. It could be drawn better, but approximately like that. Then what are the important parts of the rectangle that we want in this problem? X and Y are the two lengths of the two sides of the rectangle. So the variables that we're using, the fixed variables, are going to be X and Y. And they are changing, as you saw in the GeoGebra sheet. Now, what is the problem asking? What dimension produces the rectangle with maximum area? So the objective function, what I want to maximize is the area. And area is the two sides multiplied together. Now, look at this. The objective function has two variables, and that's not allowed in Calc 1. What do? You look for constraints. What is the constraint? Constraint is the length of the wire. How do I put that mathematically? Length of the wire, as we discussed it with the GeoGebra sheet, is actually making the perimeter of the rectangle. So the length of the wire, which is 10 centimeter, is equal to 2x plus 2y. Now that you have the constraint, solve for one of the variables. Let's say I'm solving for x. And so 2x is equal to 10 minus 2y. And therefore x is going to be 10 minus 2y divided by 2. That is 10 divided by 2 minus 2y divided by 2, 5 minus y. Now, in the objective function, replace x with 5 minus y. So I have y equal to 5 minus y times y. If we remember this from pre-calculus, then we would distribute yn, and we end up with a quadratic function. In pre-calculus, we can find the maximum of a quadratic function. Again, the coefficient of y squared is negative, therefore this quadratic function is basically looking downward like that, and then there is an absolute max for it, and so we can find that. But we're not doing that in calculus. At this step, we're not using that knowledge. We're just using the derivative knowledge of calculus. So what is the derivative knowledge? So take the derivative of a. Why am I doing this? Because I'm going to use one of the three methods that we mentioned in the beginning. So a prime of y is 5 minus 2y. Then find critical points. Whichever method you're using, the critical points are needed. So 5 minus 2y equal to 0, and it gives me y equal to 5/2 is a critical value or critical number. And so at this point that I have a critical number, I have to decide between the closed interval method or first derivative test or second derivative test. Let's remember, what is the domain of this function? The domain is, let's go back to a of y. Y cannot be more than half of the length of the wire. If you remember the picture, when we have one side equal to half of the wire, and then area becomes 0, and you can't do better than that anymore. So, and y cannot be less than 0, so the domain is basically 0 and half of the wire, length of the wire, which is 5. Oh, this is nice because this gives me a closed interval method. All I need to do is evaluate a at the critical value, critical number, a at the endpoints, and compare. When I plug in a equal to 5/2 in here, a at 5/2, I'm sorry, in here. So if I plug in y equal to 5/2 in there, I get 5/2 times 5/2, which is 25/4. If I plug in 0, I get 0. If I plug in 5, I get 0. Again, function is continuous. I check the two endpoints and I check the critical value, and I figured out that the maximum area is attained here. That is, now I have to figure out what the dimension that gives that maximum area. I found y equal to 5/2. All I need to do is to go back to the equation that I had over here for x and find x. And so this is the dimensions that we have for x and y.